We are ready to get started. So we are all probably very much excited how the top performing teams did their tasks. Like maybe there was a similar solution than some of you did, maybe it was something completely different. So now we are going to look into how everybody was working out on it. And before we do, we will just give a mini recap of the task, and this just saves your time to then not afterwards have to reiterate the task because everybody then remembers. So overall, we had 3 tasks, all in this area of trustworthiness and generative AI. And the first task was about the data usage cardinality, or the DUCI task.
Okay, so let's walk briefly through these tasks. So first, we gave you training data set, and then we ask you how much of this actual data set was used to train a given model. So here, we ask you to give a continuous score from 0 to 1 for each model to estimate this proportion of data set which was used to train the model. And then we gave you this mixed data set and also 9 models. 3 of them were less than 18, 3 less than 50, and 3 less than 152. And then for each of models, we ask you to give this DUCI score in this range from 0 to 1. So we also provided, apart from this mixed data set, also population data set that you could also use. All of that actually came from, in this case, CIFAR 100. And then the score was just mean absolute error. So we just compared the ground truth score that, of course, we knew from training the models, and then subtracted your estimation. And then we averaged these MAE scores across these 9 models. And then task number 2.
That was about the PII extraction. So we were talking about the fact that it becomes increasingly dangerous that these large models memorize data that they are trained on. And what you were given in this case was a large multi-model model. So it was a model that was trained on some image and on some question answering with that. So the answers were in the image during training, and they were not in the data that you were supposed to label then. So basically, instead of having this like model able to read from the data, you were given this data without any of the PIIs, and your task was then to evaluate what this PII ultimately was. And therefore, we did not only provide you with the target model that you were supposed to extract the data from, but also with a shadow model that was trained actually on the exact same data, but without the PII present. And what you had to submit was a CSV with 3 columns, the ID of the sample, the type of PII that you were extracting, so either the email address, the credit card number, or the phone number, and the string that represented your extracted data. And the score then was a similarity score based on the normalized Levenstein distance, where if the similarity between what you extracted and what the model actually trained on is 1, then you were able to perfectly extract. If it was 0, then it was a non-successful extraction. And the Levenstein distance, just as a reminder, gave you the smallest number of edits that can get you from one string to the other. And that's the example we saw here. And ultimately, you submitted every 5 minutes, and the score was then calculated as an average over all the samples from the test set.
Perfect. And then we have the third task, so about watermarking detection. So we gave you pieces of text, and we ask you for each of these text pieces to label either this text is watermark or not. To be precise, you had to give a score, again from 0 to 1, for each of these text sample, where a score above 0.5 was that indicating that this text actually was watermarked, and below 0.5 threshold, the text was clean, meaning non-watermarked text. And here the score was true positive rate at very low, in this case 1% of the false positive rate. So we discussed how we compute this score. So your goal was to achieve as high as possible this TPR, true positive rate. And then here also we gave you train and the validation samples and the final test split that you had to actually assign these scores to. And final submission was just ID and score. So for each of these text pieces, you had to just give us this estimated score. Okay, so regarding the jury, so we have here amazing professors here from the University of in Warsaw, from Politechnika Warszawska. So Tomasz Gambin and Piotr Gawrysiak. Let's give a round of applause. So thank you for coming, and thank you for helping us to assess these 6 best teams. We really appreciate that. And apart from also our distinguished professors, also we have CISPA team. So here they sit in the first row, also in the second row. You also can raise the hands. So also they will also help us to assess your code, your presentations, and then to finally decide on the best 3 teams who will. So it's actually the best 6 teams that, according to our scoreboard, had the highest scores per all of these tasks and the overall score. So we go with this order of presentations. I think that, okay, sorry, I think that
There's a swap, right?
There's actually, this is actually previous version, sorry. So I think that I will just give to batch norms, I think, the stage. So, okay. So can batch norms actually come? I think they were just actually.
And one thing is I will be taking the time. So you have 6 minutes in total, out of which I would recommend allocating roughly an equal amount of 2 minutes per task. You will be seeing me sitting over there, and I will be waving to the speaker, like to show 2 minutes have passed, 4 minutes have passed, and then like at 6 minutes my alarm will go off and we'll push you off the stage for fairness for everyone. And yeah.
Okay, hello everybody. Our team name is Batch Norm Study, as you can see, and maybe not to bore everybody with a long story, let's get started with the interesting part, being the first task. So, Stash, please.
Yes, I was almost happy not to see our team name in the top 6, because this might be the most vibe-coded presentation ever. So, slides are sort of consistent, but really last second, so I'll just read from here. So for the first task, the baseline was just moment matching on accuracy and just the standard clean unbiased estimator. The actual improvement that got us the best score for this task was using 2 miscalibrated estimators per target, using one estimator's own output as the blend weight. So this was taking a low P to a trust conservative and a high P to a trust aggressive. Then we used the per target adaptive blend of these 2 miscalibrated estimators whose biases pointed in opposite directions. And the blend weight was just one estimator's own output. Low P targets trust the conservative estimator, high P targets trust the aggressive one. Next slide, I guess.
Yeah. Next one.
Okay, and then for task 2, for the baseline, we just used Olmo and Lava HR and just really overfit using the VQA. We also used greedy decoding with 64 tokens, just so the training would go like a little bit faster with a feature cache. There were a lot of tricks with just regex and trying to parse the numbers and PII properly. And then we were sharding this across 4 GPUs, so we were able to train pretty quickly. Next slide. And so the improvements that we made that were very slight and didn't give us much over the baseline, we're just using the shadow model outputs as priors instead of 0 padding. And this was from the Pinto 2024 paper using sampling and shadow contrast ranking.
Okay, and for the first task, we tried about 100 experiments, training custom models, trying to measure the perplexity if you remove some tokens or if you even stitch together several sequences. And I would be glad to say that it worked perfectly. Unfortunately, it did not. So what we ended up doing, and what actually worked for us, is probably the data science most favorite thing, aka just training a huge ensemble of random features and hoping that it works. So for the final solution, what we ended up with is an ensemble of 4 separate learners, each using slightly different classification technique, or rather scoring technique, and different parts, or rather representations of the text, be it word engrams, chart-based engrams, and the whole text, of course. So that builds us the first ensemble of features, which we then also compute per smaller chunks, like separate sentences or just short excerpts from the text. Over that, we calculate 13 of like the most basic features, be it main, STD, means, some quantiles, and so on. And it gives us the baseline. But what actually made it sort of work is what we coined the tail risk features, which is basically taking the training set and trying to see if a particular model is incentivized to classify a watermark text as a clean with high confidence or the other way around. And this way we built two subclusters during the training. And the additional features are actually just the average scores towards these clusters that tell us how, in theory, unsure the model is about pretty much everything. So then we also weight them, almost hand-tuned, just three floats, trying to weight them. And in the end, we just train an ensemble of XGBoost on different subsets of these features, which in the end gives us not the best solution, but a pretty stable one, achieving, if I remember correctly, 0.18 something on the final leaderboard. Yeah, and I think that's it from our side. So thank you for attention, and please, your questions.
So now we'll be taking questions from the audience and from the jury.
Just a very short question, because probably you told that, but I actually didn't catch it. For the watermarking exercise, you started. I mean, for the first try, you got the text and converted it into chunks, right?
Yeah.
What was the length of the chunks?
It's verbal, so for each of them, I put it on a slide. Oh, sorry. For each of them, I put it on a slide. So, like for one, it was 4 to 6 engrams. For the other,
okay,
3 to 7, and so on.
Okay, thank you. And by the way, please remind me what's the length of the documents or text?
I think on average it was something like 190 characters.
Okay,
Yeah.
so something like
Not huge, not tiny.
Yeah.
Thank you so much. There was another question.
Thank you for your presentation. I had a question regarding task 1, and you have got a pretty good score on this task. And you mentioned you used the accuracy of the model as your indication of membership, right?
Correct.
And also, you mentioned something miscalibrated. I wonder if you could explain more on this miscalibrated part and what was exactly meant.
So the idea is we had sort of like a more conservative estimator and then also a more aggressive estimator. So for the more conservative estimator, we focused on like the low p-values, and for the high p-values, we're focusing on the high trust aggressive one. I'm not sure if that helps.
Conservative in the sense?
Would have to get back to you on that.
Thank
But thank you for the question, Nima.
Awesome. So I think we can thank our speakers again. And now we're asking Team 5.
Yeah, so hello everyone. I'm going to be presenting our solution for task 1. So essentially what we try to do first is like from the paper, which is was called "How much did you steal of my data?" So we tried to, which exactly does the extraction of the cardinality of how much of the training, basically a target data set was used in training a model. And initially I tried, so they had an implementation, but for text, so I tried to make it into an implementation for our images. It worked, but not that well. It initially gave us good estimations of the cardinality used, but I later had to implement further kind of heuristics. So my idea was, since we have this population data set that the target model has never seen, then my assumption was that basically the model would behave the same on this population data as on the elements in the target data set that it has not seen yet. And so I tried to implement multiple similarity heuristics to see, for example, the confidence level of the target model on the population data and compare it to basically how it does on the data set that we were given. So for that I used it was the multi-K percentile, the population z-score, and also some additional deltas that I had lightweight for, just to also make sure it works. And our final result was this p-hat, which is basically a weighted average, not a weighted average of all these heuristics that I have implemented, each using basically with the given importance. So for example, the implementation from the paper has the higher weight, then the z-test and the multi-K percentile had the second most important weights, and then the other ones had half. And this was basically the way I tried to infer how much of that training data set was used in the target model. Yeah, so this is the whole framework, and I think we can now present for you our solution for tasks 2 and 3.
Okay. So don't worry about this slide. Those are just some sample solutions we actually got for task 2. This slide is probably more than enough because unfortunately task 2 consisted of our team effort to try to make the model run for about 24 hours. And during those 24 hours, we managed to do that for about we managed to run it for like 2 times after it broke again. But during those 2 times, we actually prompted the model to please give us the information on the images. And it actually gave us enough information to achieve about 0.5 score on the leaderboard. So that's our solution.
Good afternoon, everyone. I'm going to present my solution to task 3. Okay. My solution was for the watermarking, basically detecting watermarking within text. So how I went about this is that initially we tried generating about 3 features per text, whereby we use a model to basically generate the entropy, the rank, and the probability of a certain text being generated by the large language model. Then to avoid having too many values, we basically generated every 10th percentile. Yes, and then as a result of that, we had about 33 features per each text. Then we basically fed these features into a classifier, and then this classifier initially we started with a linear regression, and then we moved to HGBM. Not sure if it's shown. Yes, but before all of that, we had a very low score whereby we tried using the GPT-2 PPL only, of which it gave us only a score of 0.08. and then this proved to be 0.07 on the leaderboard. And then later on, we tried to use another model, which was OMO, of which this turned out to like actually boost our CV score to 0.1, and then this gave us 0.14 on the leaderboard. Yes, so this gap was actually quite small, because initially during the test, we actually got a 10 times gap, but then through manual testing, we actually managed to actually trim it down. And then later on, I noticed that my score was still too low. Basically, the model would actually perform well on the CV score, but then not on the leaderboard, because this was overfitting. The model was basically.
Okay, we have to finish. It's
Yes,
6
okay.
minutes done. We have to keep timing for everyone the same, so it's fair. Okay, so thank you. So. Okay, thank you very much. Now we ask questions. Any questions?
Thank you for the presentation. I was wondering for task 3, how did you train the classifier? Like, how did you gain labels?
Okay, so with the labels, we basically used 3 models, which was the OMO, and the Llama 3, and the GPT-2, to basically generate these 3 features per every 10th percentile token. Then we use these features in the text to now later train the classifier. Okay, basically these features were generated on the training data. Yeah. So now we sort of use that to train the classifier and say that, okay, this is watermarked, so how closely, so like this is what it looks like. Yeah. And then that's how we train the classifier.
Okay.
Yes.
Thank you.
Thank you.
The question for the third task itself. In the previous slide, you showed that you are using cross-validation, and can you tell if the cross-validation data set, the data samples, were the same as the validation samples that we provided, or were they different?
It was the same.
Okay, so then why do you think that the train or test have different watermark keys?
I think it was because there were cases whereby it would sort of learn the training data too well. So now after uploading it to the leaderboard, it would be different. Yes.
Okay.
Thank you.
Thank you.
Are we having any more questions from the audience? All right, then let's thank our speakers again.
Okay, so hello everyone. Our team is Troopers, as you can see, and my name is Olivier, and I will be presenting the first task. So, my idea for this task was kind of, I want to present this idea. I had many ideas, but this one seems good to present. We have the models and we have the data, so we can train the models on the known amount of data. So, for example, I have one model and I'm training it on 0% data, then a quarter, then 50%, 75%, 100%. And the idea is that the more data I provide, the loss will decrease. And my assumption was that it will be a linear model. So then, when I have this computed locally, then I can take data, input it in the black box, and measure the loss at the end. And later, I have this linear model computed locally, and I can just take the loss I got and just apply it to the linear model, and then get the my assumption of the amount of data it was used to train the model. So yeah, and I guess that's it. And so the next question.
Yeah. You can click for me, maybe.
Yeah,
So for the second task, the first thing that we did is to take the training time answer templates, cut it right before the redacted text, and input it as an assistant response, so that hopefully the LLM just fills out the rest. And it served as a sort of baseline for our future improvements. Then we tried 5 different prompting techniques and we found out that the best one is to just ask kindly to give the data from the data set. And we also made some improvements based on fallbacks. So if, for example, an email from LLM is not a valid email address, we just compute it from the name, surname at example.com. Yes, and
to make fallbacks even better, we employed popularity vote between all our prompts, with exception of obvious placeholders, which are 0000 or 1234 1234. And with that popularity vote, we broke through 0.5 barrier. It was important because there were different input channels for the email, phone, and credit, with email being mainly text-based, with strong encouragement with name and surname, and with credit and phone it was mainly image-based, so the models had more problems with responses.
Okay, so moving to the watermark detection task. So we tried many different approaches, around like 50, and that's our best solution architecture. We tried to make kind of a giant ensemble, starting with feature extractors from different types, because we could choose one good extractor, but there are different watermark families that could be omitted because of that. That's why we used many weaker signals, but they are complementary to each other. And we used logistic regression to learn the weights from these vectors from extractors. And we passed it to the two of the heads. And then the heads calculated the score, and the score was passed to the ranker. And the ranker generally took the scores, but it couldn't like combine them together because they could have different distribution. So we used average ranking to combine them. And it worked generally if we have from both the heads inputted that the text is watermark, then it increases score of it and puts it higher in the order to match it with TPR, FPR metric. And moving forward to the heads, how they work. The first head A, used full next token distribution of large LLM, exactly OLMO 7, and it checked like how scattered are the tokens, or the tokens it chooses the highest probability tokens all the time. And the head B is generally keeps the balance style. We use different combinations, multiple combinations of tokenizers and green fraction settings, and it generally does. For each combination, we use each token as set as green or not, and then we use that data to train the model to learn which setups it should trust to. And here we have also drawbacks and limitations of this solution. So the complementation was good because it allowed us to like remove the errors. One model had some errors, the other had some errors, and it just combined them, so it removed them. And also this re-ranking allows to increase the FPR because it's more aligned with the how it works, because it just puts the order of the watermark and not watermarked points in the order. And I think we are missing the time, so that's all.
Thank you.
Thank you
very much for your presentation.
Thank you.
Okay, any questions from the audience? So we have one question over there.
Thank you for your presentation. I have a question for task 1. How many samples from the population set did you use to train the reference models?
If you mean I think, so I used, so as I mentioned, I used some amount of like percentages of the data set, right? So we had two data sets and I used both of them because I was trying like both data sets, and I used like 0% first, right? And then some amount, so a quarter of the data set. So yeah, so.
But you merged both data sets in one?
No. First I was I was trying first on the first data set, and I was trying second on the second data set. I was trying to see if taking different data sets, because like I was assuming that it will be linear, so I was trying to see which one can like approximate the linearity the best. Yeah, and it's also it was also depending on the model, because for example the first model, I think I got almost perfect linear model. So it was like the data that I showed, it was a real data, so it was like almost perfect line. But for example for the bigger ones, so 50 and 152 models, I mean the RES 50 and RES 152, the linearity was worse. So yeah, so I think like as you can see from the scores, it did not work, because I think only for the first model it was really like linear. Yeah, so this is like the actual data.
Okay. So because I was just curious about, for example, when you trained half of the mixed model, if you maybe use also half of the population set. To make the proportions the same, or maybe make the overall overall number of samples in the training data sets the same.
Yeah, I think I know what you mean. Like I don't know if I did that. I think I did. I did not. I did not do that. When I'm thinking about it right now.
Okay.
Yeah.
Okay, this is a good question. Any comments? Questions? Then for also task 2, did you also use shadow model in task 2?
No, we did not at all.
That's it. Amazing. Okay, no more questions. Okay, thank you very much.
Okay, so I'm Kekim from Advanced Persistent Thinkers, and let us start from the task that we are only one of these things about. The first task was for us a bit of a disaster. I could describe what we ended up with. That was a system with multiple shadow models trained with different proportions of the data sets that were used, that we then extracted a dozen features from, tried to calibrate on the multiple shadow models which mix of the features was the most reliable for detection, and then also select the shadow models that were closest to our initial guesses about the final proportion of each model. However, as you may realize by our final score, this solution just straight up doesn't work, doesn't generalize, and we're actually not sure which one did, because the solution that got us to the podium for this task for most of the hackathon was basically lucky guessing, or as it turns out, unlucky guessing, because we after guessing the initial distribution and playing around with different metrics that we're not sure even which one produced the final score, basically got no further feedback for this task, never beating our initial attempts. So,
okay, so I want to explain how we approached second task. So for each sample, we generated 20 candidates with temperature sweep, so with different temperatures to achieve different answers. And so we also used a prompt technique called prefix guided generation. So we haven't asked as nicely as the other teams. We just made the model respond with starting example, the credit card is to trigger a recall in our model. We use also self-perplexity ranking, and so we chosen the lowest target model loss, and also per digit voting, ensemble across multiple runs, and also employed Lyra from Carolini et al. So I'm to move to third task.
So our approach for the third task was to extract per token features from free references LLMs. We used the Gamma Free 4B as the new model. We used the GPT-2 medium as the legacy one, and we use a Distill BERT. So per token, we calculate 6 channel features such as log prop, rank, entropy, top 1 prop, margin, and price gap. Then we put it through our CNN with 4 parallel conv branches plus residential blocks. Small kernels catch local disagreements. Large kernel catches long-range patterns, so we make sure that the watermark is visible at every scale. Then we go through multi-crop TTA, 3 different 384 tokens windows per sample, averages our predictions, but we do not rely on a single models. We assemble 50 models, 5 seeds, 10 faults cross validations, and mean predictions across all these models kills random variance and produce a stable, reliable score. Our key finding was that the GPT-2 medium emerges as a critical model. We have some evidence that it might be the base model used to generate the watermark data set. And here is a quick overview of the architecture.
Okay, thank you very much. So now, questions, okay?
Hi, thank you for the presentation. So for the watermarking task, what other models did you try outside of this BERT, Gamma, and GPT-2?
A lot. Quen, there was a Mistral, I would say.
Olmo?
Olmo might be. A lot. Actually, you just try everything and you catch the golden fish.
Yeah, okay, thank you so much.
Thanks. For the second task, did you use an sanity checks for the PII extracted, like regex or something like that, to check whether the answer is really PII?
Yeah, sure. We did some regex, which was really crucial for this task. And also I had to employ also some check for credit cards. You can check if a credit card number is valid, but actually it was randomly generated data, so no credit card number was valid at all.
No such chance.
Yeah.
No free lunch. Any more questions? Okay, if no, then let's thank the speaker again. Thank you very much. Thank you.
So I'm going to talk to you about the first task that we solved. So as you know, we have 9 trained models and 9 trained image classifiers and 2,000 candidate images. And our first solution was to use the shadow models. And we tried, but the issue with shadow models was that it didn't match the target model, so it didn't seem like a good solution in our case. So what we did instead was that we focused on each model. And so we just listened to each model. What happened was that, so we show a model 2,000 images, the mixed setup between the seen and unseen images. And also we showed it another set, but this set is a set of the images that we know the model has never seen. And then we started comparing them. And that comparison gives us the result and the ratio that we were looking for. And here in the left side of the slides, you can see some of the results we have.
Okay, and I will cover quickly the second task. So we basically were validating everything against the validating set, and initially we also did a quick script to remove all of the PII data, so then we have a source of truth, so to say, and the redacted images. And yeah, it was also placed in different parts of the image, and so we had a script that kind of spots it and removes it. Then we noticed that there is an amount of data that is actually not redacted in the training set, and it was our, so to say, initial edge. But then it was also revealed in Discord that it's actually not going to count, but still. And our main, so to say, edge that we got was that our model liked to spit out the, let's say, the default hallucinations, like the same email for any kind of input. And so the idea was that we had a filter that, like, any candidate, like any email that shows up multiple times for different profiles, it means it's hallucination. And we were just removing this simply. And also we were rescoring each candidate by asking the model the same question with swapped username, like, let's say, John Smith, right? And basically that's it for the task 2.
Yeah, and finally for the task 3, for the watermarking one, so here's what we actually built. The core idea is simple. Watermark text is slightly less natural than human writing under any decent language model. So we use LLMs as detectors and not as generators. So we ran like every text snippet through 4 different auditor models, as we call them, Gemma, GPT-2, Quen, and Gemma 4. And from each one, we extracted 17 different statistical features.
Yeah, so we had 17 different features from each of these models, and these contain information like the token entropy and how often the most likely token was ignored by the model. So yeah, so we had these 17 features, and in aggregate we had like 68 feature vector in total for a token, and then we trained a gradient boosted tree model, basically 64 different gradient boosted tree classifiers on different random seeds, and we averaged together the scores to get the final classification. Yeah, and that was our approach that got us into 5th place.
Yeah, thank you so much. Yeah.
Any questions?
Yeah, hi. So actually, was it again the third task? Was it like a small tiny improvements all the way, or was there something that just made it like made you go to the top, like just one change that did it?
It's not going back.
It's not going back.
So can
Was
you?
there like one breaking point that made you go to the top of the leaderboard, or was like small improvements?
We started with GPT-2. We can say that. Yeah.
We started with the smallest model, GPT-2 large, and then we also tried with an even bigger model like the Gemma. Yeah, the Gemma 2. Sorry, the Gemma 4 billion. Yeah, and then we moved to, and then we saw an improvement in the scores, and then we decided to further scale it up. And then we tried with the Quen 2.57 billion model, then even further decided to scale it upon to a 9 billion model. And yeah, it even further improved the results. And then we used that, and then we got into a saturation point, and then we decided.
We somehow observed that the incremental approach of adding, one model after another gradually improved the score, and then we built the layer naturally.
for the architecture. Yeah.
Makes sense. Thank you.
Yeah.
Question for task 2. What was your strategy for using Shadow LLM and the other one?
Yeah, so we use the Shadow LLM model to find the perplexity difference between the target model and the shadow model. So the lower the value is, it implies that the model has memorized the information. So that was the metric that we used to identify. So yeah.
Any more questions? Okay, if not, let's thank the speakers again. Thank you very much.
Hello, my name is Aleksander Radanowski. I'll tell you something about first task from our team. We have 45 reference models, and that was trained like a target model earlier. We used 30% of random data from mixed data set and population data set, and we have overall 15 averaged models for every ResNet. Then we have we made inference for target model and reference model on all mixed data and population data. So it allows us to calculate relative confidence of reference model. It tells us how many percent of unseen data Z have confidence lower than data X. In target model, we don't know what data X is, but in our reference model, we know what X is because we trained it on mixed and population data set. Then as we calculate this relative confidence of reference and target model, as I told, in reference we know what unseen and seen data was, so we calculate mean relative confidence on seen and unseen samples, and average as of the relative confidence of target model. So here we assume in fraction estimation that it's some rewritten equation of linear approximation, and we assume that if S at t is bigger, then p hat is also bigger, and it's some linear approximation where p is 0, then it's equal to mean relative confidence on unseen samples, and if it's 50%, then it's equal to seen samples.
Okay, and I will talk about task 2. So our approach is pretty simple. We take the prompts from the test training set, the redacted set with images, and prompt both target models and reference models with identical prompts for each example. And we do batch decoding, so for every prompt we generate many answers with different parameters of decoding. Then we extract the PII information appearing in the answers with regex, and then all of those candidates and reference generations we use for the unified score to so that we can have a final PII. So the score consists mainly of the log ratio between counts of unique samples generated by the target model and the shadow model, and then we have additional score elements with lower multipliers. So we also evaluate for how many decoding setups of different temperatures the answers were repeating. Also, we give the bonus if the generated PI was early on the answer, so just after the initial prompt. We also give small bonus for the log confidence of the target, and for the final answer we do some sanitization and regex to keep the correct format.
Okay, so the third task at the beginning was pretty similar to the other things. So we basically took some LLM classifier and took some perplexity features from out of them, then adding some more classifiers to get more features, but there was a plateau. The next step was to take some naive bias features, but still all these features were treated as a single logistic regressor. Out of we took a single digit, a single probability for each sample. And the other breakthrough was where when we per group ensembled it, like separate classifier per different model group, and we then weighted them geometrically. And the final step is to split LMs into different architectures, and the final one was to take the fourth signal from to fine-tune a Distelbert model and treat it as a fourth group. So eventually we had 4 independent signals instead of a single one. The first one was from 42 features, 14 features from each LM, Wen, Llama, and Pythia. Okay, so 4 signals, then we score each sample. We then
stop yeah. So that we are fair to all the teams. Okay, let's give a round of applause.
First task, you said that you trained on the mixture of the mixed data sets and the population data sets for the reference models. I was wondering why you did that.
Why you got a reference model?
No. So here it says that you trained the reference model on the mixed data and the population data, but the target model was only trained on the mixed data, right? So why did you decide to follow the reference model?
Because it's simulation of how target model was trained previous. We simulate that mixed data is something that the model seen, but population is something that it for 100% it didn't see. So it's something that we can compare this to our backbone model and our given target model.
Thank you. Okay. So task 2. I don't know if it's that important, but I found it interesting. What were the obvious artifacts that you penalized, and how did you penalize them?
Okay, so the obvious artifacts were something like emails with numbers on both sides, so like 112 at 112 or something like that, or just a wrong count of the numbers for the credit card, or the phone number without plus one at the beginning, so something like that.
Okay, thank you.
Okay, any more questions? Apparently not. Okay, so let's thank again the speakers.
Thank you.
So how we are going to move on now is that a jury is going to consult and to add a ranking to what has been on the scoring board, and then to determine the final ranking of the task, which also will tell us whom we're going to see again in roughly 2 months from now for the big final at CISPA.
So please stay in the room, and the jury will go out from the room, from the aula, for a few minutes. So we will be asking you to just stay here, and we will be back in a few minutes.